Okay, everybody, boys and girls, ladies and gentlemen, people, we are looking at Unit 4, Worksheet 2. Hopefully you completed it to the best of your ability, and we'll kind of just go through and I'll maybe tell you some things about it and make sure you're on the right track. So number 1, how can you tell if an object is experiencing balanced forces versus unbalanced forces? Now, people, this is something you were supposed to already know for the last quiz we took, so I'm hoping that you still know, and if you didn't then, I hope you know now, that when balanced forces, oh my gosh, that's moving, whoa, 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 I don't know if that moved around on your screen or if it's just mine. Holy cow. Hold on, I need a pen. There's a pen. I got the pen. Pen. There we go. Balanced forces versus unbalanced forces. So hopefully that you'll know that when forces are unbalanced, I'm going to say that's 1 and that's 2. For 1, when they're balanced, we have no change in motion. Boy, this is going to be tough. This is, oh boy, that's some big writing in a little space. So there's no change in motion when forces are balanced. That means it could be at rest. It could be in motion with a constant, oh my gosh, that's a C, constant velocity. If we have unbalanced forces, then there is a change in motion. Is a, oh my gosh, this is writing terribly. Change in motion. That's, oh my gosh, this is awful. Again, there is a change in motion. And, here, furthermore, so many of you on the quiz forgot this part. There is a change in motion in the same direction as, oh boy, do you know what the rest of this phrase is? In the same direction as the imbalance. Boy, this is just a big writing in a little space. That's terrible. The imbalance. So, again, if the forces are unbalanced, then we have a change in motion, and this is critical, it is in the same direction. The change in motion is in the same direction as the imbalance. Now, by change in motion, what are we actually talking about? What do I mean when I say change in motion? An acceleration. Hopefully you know that. Oh my gosh. Oh my gosh. Whatever. You can't even see it. I can't write it. You can't read it. I don't know what's going on. All right. Where was I? Oh, yeah. Number 2. The Spot family. Spot family has been having some serious issues with their car lately. Everywhere they go in Napoleon, they leave a trail of oil drips on the street. Examine the patterns below and determine if the cars are experiencing balanced or unbalanced forces, and give reasoning for your answers. So the first one, can you tell whether that's balanced or unbalanced? I hope you can tell that it must be unbalanced. Must be unbalanced. How do you know? What do the oil drips show us? They're getting further apart. When the oil drips are getting further apart, that means that the Spot family here is not traveling with a constant speed. That means they're getting further in the same amount of time as the drips fall. So this could be like a motion map, and if it were like a motion map, then what's happening is the arrows are getting longer. Oh my gosh, as you go across, this is terrible. There, something like that. So it's showing us that there's like a motion map here, and so we have an acceleration that way. So it is accelerating. I'm just going to abbreviate. Second one. I don't like the, oh no, that's, okay, so anyway, second one, I would say balanced. How do you know it's balanced? Because those oil drips all look to be the same spacing. Same spacing on the oil drips. There we go. My pointer. I got my pointer back. So same spacing on the oil drips, meaning that they're not speeding up or slowing down. There's a consistent spacing between the drips, which means we have no acceleration. No acceleration. And the last one. It looks like the oil drops are getting closer together. So if this were like a motion map, we'd be looking at arrows. Oh my gosh, what is happening with this stupid pen? We'd be looking at arrows that look like they're getting shorter as time goes on here. Shorter arrows, meaning it's slowing down. That means we're talking unbalanced. And how do we know it's unbalanced? Because it is accelerating. I can't write the whole word. Too much space, or too much size in my writing and not enough space. So, below here, which of the three diagrams here represents each of the three A, B, and C above? So, I hope that you're thinking what I'm thinking, and that this one here is unbalanced to the right because there is an acceleration to the right, and therefore A has to be what? Hopefully you're thinking the third one out here. So that has to be A. Has to be A. And why do we know that? Because it's unbalanced to the right. Notice there is a force to the left, but the force to the right is bigger, meaning there's an imbalance to the right, the same direction as our acceleration. Moving on. Scenario 2, or B, I guess it is. So for B, it looks consistent. We don't have an A. There is no acceleration for this one. So A is 0 here, meaning which one of our scenarios below here is going to apply? I'd say the one where everything looks balanced. Up and down is balanced, right and left is balanced. We have balance all the way around. And then we have, of course, the last one goes obviously with the last scenario. We have only one left. And on this one, since the arrows are getting shorter as we go, that means we have an acceleration in the negative direction, or to the left, which then coincides with this force diagram because we have a force to the left. There isn't one to the right to balance it, so our imbalance is left. And so we say that's for C. Oh boy, now we're supposed to label the names of the forces above with the names of possible forces that could be present in these scenarios. Be sure to use agent-object naming. Oh boy. Well, this looks like it could be force of gravity on car. Is it going to be force of gravity on car in every diagram? Why, yes it is. Force of gravity on car. Oh my gosh, this writing is awful. And again, once again, force of gravity on car. All right, there's that one. That's an R. That's terrible. This is awful. Okay, so there's the first one. Now, each of the diagrams has an upward force as well. They all have an upward force. And so what do you think those are called? Well, most cars, I think, travel around on the streets or the roads or whatever you want to call it. So I'm going to say that that must be the force of road on car. I'm running out of room. Force, oh my gosh, of road on car. This is, oh my, oh jeez. Force of road. I guess I don't need the word of in there, but I did anyway. Force of road on car. Oh my gosh. Okay, now there's more. Scenario C. I'm going to say that's a force of friction on the car. Force of friction on, oh my gosh, on car. For C. Now, for B, it looks like we have two different things going on. We have, there's a force that's making the car go forward, but then there's also a force that's making the car go backward. So we have two different forces that are happening in opposite directions of each other. So what are these things caused by? What do you think is resisting the motion of the car? Probably the same thing that's resisting the motion of the car back here, the force of friction of the road on the car. So I'm going to call that the same thing. Force of, oh no, friction. Oh my gosh. Okay, you can't read it, whatever. You heard me say it. Force of friction on car. Now, before I even move on to the other force that's in this diagram, is that the same force that we have on this one? Is that also a force of friction that's opposing the motion of the car? Sure. Okay, so I can name that force of friction on car too. Oh my gosh, force of friction. I can't write this small. Force of friction on car. Okay, just deal with it. This is terrible. It started off okay and it got worse. Okay, now I have two more forces though. I have the force here that's a force on the car in the direction it's moving, and this as well is a force that's on the car in the direction it's moving. Now, I don't know what you called it. You probably called it, well, I don't know what you called it. You may have called it force of, I don't know, engine or wheels, or I don't know what you called it. But here's what we have to think of. What is the car in contact with? Like in this picture, is there anything touching the car from the outside, touching the car, besides the road? What are you answering for that? Is there anything else touching the car externally from the outside besides the road? The answer to that is no. So that means the other force, this force here that's in our diagram, that should be in our diagram, that is in the direction that the car is moving, in both cases, it's actually another force from the road that's in the direction that the car is going. I can't really explain to you, like, I know that probably doesn't make much sense, but that's the case. Because think about this, if the road was a sheet of ice and you hit the gas pedal on the car, what are the wheels going to do? They're going to spin in place because there's no friction force between the wheels and the ice. However, there isn't ice, this is a road. So the road itself is pushing back on the wheels of the car, propelling the car forward. So I'm going to say that it's the force of road on car. Force of road, that's an A, on car. That's just what it is. Deal with it. I can't explain any more right now. I'm sorry, I can't do it. Now we got to get the backside. Okay, backside. Here we go. Now we got to work on some summations. All right. So what we have here. Oh no, this thing is in my way. The toolbar that you can't even see because it's. Oh, I can move that around. Well, that's crazy. Let's see here. Scenario 1. Or I should say is A balanced or unbalanced? I hope you see that it's balanced. I'm just going to put B. Is scenario B balanced or unbalanced? I hope you see it's unbalanced. Okay, Jiminy Christmas, this is ridiculous. I hit a button by accident. You have to accept my apology. So B, again, unbalanced. C, that looks unbalanced as well. And it looks like at this point, yes, we have balance here. We have equal up and down. We have equal right and left. That's balanced. Here, we have equal right and left. We don't have equal up and down. Here we have equal up and down, but we don't have equal right and left. So what do we do with that? Well, we're going to have to write some summation equations based on what we see in the diagram here. So in the X, in scenario A, it looks like we have force of push, which is a terrible name, plus force of friction. It's a terrible name because it's not, push is not an agent. The agent has to be an object, a thing that's actually doing the pushing or pulling. And that's going to equal 0 newtons because we know that, because it's balanced. What is happening right now? This is, oh my gosh. This thing is there, okay. You don't know what's happening on my iPad right now. You can't see it. It's probably a good thing. Okay, forces in the Y direction. We have force of table. I'm touching buttons that I shouldn't be touching. Hold on. You're just going to have to bear with me. This is terrible. Force of push plus force of friction. Let's see, force of table plus force of gravity. I'm just going to, little g. And that is also going to be equal to 0 because it's balanced. Oh, I'm not even going to put any numbers in. You can put numbers in and do that yourself. I don't even care at this point. I just got to get through this. So, number 7, show what the summation of forces is in scenario B for both the X and the Y. So the X, we have force of push, which is, again, a terrible, terrible name. It'd be force of hand or force of, like, whatever. I don't even know. Plus, apparently there's another force of push. Okay. Stupid. Equals 0 newtons because they're balanced. The Y direction, we have force of cable plus force of gravity. That does not equal 0. So I'm just going to put equals, and we got to figure that out. There's a little question mark there. You can put some numbers in, you can figure that out. Hopefully you can figure it out. Incidentally, I would say that it's positive 20 newtons. When you substitute in everything, you should get positive 20 newtons for your total summation. And number 8 here, the X, I have force of friction. I'm not even going to write the word out. Force of friction plus force of push. I'm just going to write F sub P. How about that? And then, equals, and again, the question mark because they're not balanced, and so they have to equal something other than 0 because they're not balanced. And then the Y, we have force of road. Whoa, that's a messed up F. Force of road plus force of gravity. And that one does equal 0 newtons because they are balanced. Now, going back to this one, the number 8, the X direction here, that looks like that's going to be a positive 20 as well for oh my gosh, positive 20 newtons for that one as well because I have 35 in the positive, I have 15 in the negative. When you add that up, positive 35 plus, oh my gosh, positive 30, this is terrible, positive 35 plus negative 15, that's going to be a positive 20. And similarly, this one's positive in this force diagram, this one's negative, and so a positive 40 plus a negative 20, that's where the positive 20 comes through on this one. So in both cases, there are going to be positive 20 newtons is going to be the total sum of all the forces in the system. Number 9, if, oh, this one, yeah, you can't answer this one yet. You don't know how to answer this one yet. Save number 9 for after you see the next video in the lab thing that, actually it may not even be after that. The lab thing may not even tell you what the answer to this question is. Oh boy. We'll have to get to that later. I apologize. That question probably shouldn't have been there. So anyway, hopefully you learned some stuff and you were able to use the information that we've learned the last couple days to be able to diagram all these things out and make some sense of it. So hopefully this helped, and we'll see you next time.